first and screen sharing. What? Okay, we are ready to start a new topic. So when I teach Comp 330, I divide the course into 3 modules. The first one is on finite automata and regular languages. And this is the second one on context-free languages and pushdown automata. The third one is on computability. So because of this highly compressed way in which we're teaching this class, what's normally 2 weeks for module 2 becomes 2 lectures for module 2. So we're going to start and finish context-free languages today and tomorrow. And then on Thursday, I will start the theory of computability, which will occupy us till the end. And that's, in my mind, at least the crown jewel. So because of the holiday yesterday, I had to cancel a topic. And after much agonizing, I canceled fixed point theory. Yeah, maybe I'll change my mind and restore it and cancel lambda calculus instead. We'll see. Okay, so the new topic today is context-free languages. So now we are exploring what happens when you increase the power of your programming paradigm. So what we had before was essentially a purely finite memory system. So you could have control by jumping from state to state. That in some sense represents control flow. And what memory you had was just whatever you could encode in your state. And since it was a finite state machine, whether deterministic or otherwise, it was still a finite memory machine. And there were limitations on what we could do. Even when we came to Omega languages, there were limitations on what we could do. But now we're going to give you infinite memory. So essentially, we're going to give you a finite state machine plus an auxiliary stack. And then in the next module, we'll give you 2 stacks. But for now, you just have 1 stack. Okay, but this is not the way to present context-free languages. We will define them in terms of grammars. So we'll call them CFLs in terms of grammars. So this motivation comes from linguistics, and it was pioneered by Noam Chomsky. Now, the way context-free languages work, so we're going to define a grammar as a way of generating strings. When we defined regular languages, we defined them in 2 ways. So the first way was in terms of finite automata or deterministic finite automata as recognizers. So they were things that could check whether or not the string was in a particular language or not. And the languages that could be checked in that way, we defined to be regular languages. Then we gave an algebraic description of these languages through so-called regular expressions. So we had a kind of linguistics way of defining the languages and an automata-based recognizing way of defining the languages. We're going to do both in this case as well, but we're going to start with how you generate the strings in the language. And our grammars are going to have a lot more structure than just regular expressions did, which was just algebra and some operations. Here, we're going to give you rules for producing strings or words. So here are the ingredients. A context-free grammar. Consists of a bunch of things. One, a set of symbols called terminals. Okay, and this will be the alphabet for the language. So this will be our alphabet. And then another set of symbols called non-terminals or variables. And this set is called V. And these are disjoint sets. And both V and sigma are finite. So even though the languages we describe will be infinite, the description itself will be finite. We'll have a special variable called the start symbol. And this is usually, but not always, S. So S might be what we call it when we're talking about a generic grammar, but in certain cases, it might be more sensible to call it something else. Anyway, it's just a name. But here we come to the important bit. A set of rules, and again, this is a finite set, called productions. And here is the format of a production. So it looks like this. Where A is one of the non-terminal symbols and alpha is a finite string containing both, potentially, both terminal symbols and non-terminal symbols mixed together. This is star, so in particular could also be the empty string. So you could take a variable and say, I'm just deleting it. And so now I have to explain, how do I produce strings like this? And I'm going to do that by way of an example. So for my example, I'm going to take sigma to be AB. So these are my terminal symbols. So this word terminal suggests that something is going to be terminated. And that's correct. That's the right intuition. And basically, it means when you produce one of these symbols, you stop there. That thing just stays around. It cannot be changed. Whereas the word variable is supposed to suggest something that can change. Okay, the variables for this example grammar is just going to be one, and it's going to be, of course, since there's only one, it's and the start symbol has to be there, it'll just be the start symbol. And there are going to be two rules. And one rule says S goes to epsilon. So basically it says you have the start symbol and then you can transform it to epsilon. The second rule says S goes to A, S, B. So you see, here is a mixed string. It has some terminal symbols as well as some non-terminal symbols. In this case, just one non-terminal and two terminals. So how do I produce strings like this? Apply any rule you feel like to replace a non-terminal with the right-hand side of a rule. Okay, so there's absolutely no constraint. Importantly, when you're applying a rule, you don't have to care what's around you. You just look at this non-terminal and say, I can choose whichever rule I feel like to replace this with whatever appears on the right-hand side of the rule. It doesn't matter what's the surrounding context. That's why it's called context-free. In other kinds of grammars, you say, I can use this rule only if I've got this thing on my left and that thing on my right. Those things are called context sensitive. Context sensitive grammars are more powerful than context free grammars. Context free grammars are much more powerful than regular languages, but they're not able to do everything. So let's produce some strings in this language and see what we get. So we start with the start symbol, we apply rule 2, and we get the string ASB. Now you see A and B are called terminal symbols for a reason. Their lives have been terminated. They just stay around and nothing can be changed. But this S in the middle, this is still an active variable. It can be changed in some way. But the surrounding context does not get altered. So the A is still there, the B is still there, and nothing you do is going to remove them. But this S, it ignores what's around it, and you just apply a rule again, and you get ASB. So this has become this. And the A and the B that were there before are still there. So if I want, I can apply this rule again. Now the AA is still there, the BB is still there, they're terminals, and I can decide, oh, I want to do rule 2 again. And now I can decide, all right, I feel like wiping out the S with rule 1. And this is a string in the language. When you obtain a string with no more non-terminals, you have generated, sorry, you have generated a string in the language. So let me stop now. This was just an explanation of how it works. Any questions? Because I'm just going to take this basic paradigm as fixed. So what's the language that I'm getting from this? So the set or the language of this grammar G is the set of all strings such that W can be generated from S. Okay, that's called the language of the grammar. So all possible generations have to be taken into account, and then you get this big set, and that set is called the language of the grammar. So unlike with DFAs, where the language is somehow defined and then your task is to recognize it, here we are generating the strings. Later on, we'll talk about recognizing them as well. There is a description in terms of machines. Okay, so what language is being generated here?
Maria says A to the N, B to the N.
Very good. So you can see this language, very simple grammar, is not regular. So CFLs are clearly more powerful than regular languages. Okay, so that is the intro. So let me do some examples. So it was originally conceived by Noam Chomsky as a way of generating strings in natural language. So for example, in English, you would have a grammar where the start symbol would be something called sentence. Other non-terminals would be things like noun phrase, verb phrase, and so on. And then you would have rules that said, well, noun phrase can expand to this and verb phrase can expand to that and so on. Ultimately, you got actual words and actual sentences. Okay. So I'm not going to give you examples from natural language, but let's look at a grammar for arithmetic expressions. So in terms of languages, context-free languages are extremely much more powerful. And here is a fact. All modern programming languages, the syntax is a context-free language. In fact, it's even much more restricted than that. But for sure, they're always context-free languages. There are languages that are not context-free. And in the old days, there were languages like COBOL that did not have a context-free grammar. But now we've realized this is a stupid idea. And every modern designed context programming language, even the ones designed by machine learning people, are context-free. Okay, so arithmetic expressions. My alphabet is going to be first the digits, there are 10 of them, then two symbols, times and plus, and two other symbols, the left and right parentheses. And I'm going to give the set of non-terminals like this. So I'm not going to call the start expression S because that's kind of stupid. I'm going to call it exp. And then from these digits, I want to generate numbers. So I'll have another non-terminal called num. And then I want to generate non-zero things. So I'll have another non-terminal called nz, and then I'll have another non-terminal called n. So these will allow me to generate integers. So the rules look like this. So this is the start symbol, exp. It's generating arithmetic expressions. In order to save space, instead of writing every rule on one line, on a line of its own. We're going to put multiple rules on a single line. If they all have the same left-hand side, we'll write it as one rule with a vertical line to suggest alternating between different choices. So here is one rule. And here's another rule, and I've written them on the same line. I've used not the asterisk, but the time symbol. And then I'm going to continue making this a long line. So a parenthesized expression is also an expression. And finally, an expression can just be a number. And then how do I generate numbers? Well, I want 0 to be a possible number. So here you see the right-hand side is a single non-terminal. The production process is over. However, I have other choices. It could be this new non-terminal NZ. The reason I'm doing it like this is because I want to allow you to write 0, but I don't want to allow you to write 0, 0. NZ can be 1 followed by N, 2 followed by N, all the way up to 9 followed by N. But not 0 followed by N, because NZ is supposed to suggest non-zero. So I'm not generating strings that start with 0. But after that, I do want to allow you to generate zeros, because you do have things like 101 and so on as valid numbers. So that's N, not NZ. And now N is kind of unconstrained. Can go 0N, 1N, up to 9N, and also epsilon. So at some point you want to stop, you've generated the number you want to get rid of the non-terminal, you have this last rule that goes to epsilon. So you do realize this is 11 rules that I've written on the same line. These share the left-hand side, so I can compress the presentation. So I'm not going to belabor this part of it anymore. This is kind of a simple grammar to just generate numbers. Now I'm going to focus on generating arithmetic expressions. To properly display derivations. So the production of a string from the start symbol is called a derivation. So we're going to have these derivations. I'm going to just do something for a minute. Okay, to properly display derivations, we will use trees called parse trees. And the whole point about introducing context-free grammars is they capture tree structure in a way that I want to make clear next. So I put actually several sets of notes, I think 7 or 8 on this topic on the web page. So in addition to this lecture that I'm writing, and which will be there as well, and the video and the audio, there are also 7 or 8 sets of notes that I've written out for you. So let us try to generate the string 2 times 3 plus 5. I'm going to do it very quickly. exp. So I'm going to use this rule. Then this exp expands to another exp. And then I'm writing a dotted line because there's a bunch of things going to n and nz and so on that finally produces 2. I don't want to waste time showing that. This produces 3, and this eventually produces 5. And if you ask, what was the string produced in the end? Well, you see, finally, we brought it down to only terminal symbols. So now we have a string in the language, and that string is described by the fringe of the tree. So you see, it's 2 times 3 plus 5. Okay. You look at this and you realize this is correctly grouped. After all, if you look at the tree stripped down, if you look at an expression tree for this, it kind of looks like this. Okay, so this is like taking the parse tree and stripping out all the non-terminal things that were there because you were trying to construct this from the grammar. But once you've done that, you can say, well, I can show this, display the string in this form, and you can see the grouping is correct here. That 2 times 3 is more tightly bound. So does the grammar guarantee this? And the answer is unfortunately not, because you can do this instead. I can say the first rule I'm going to use is this one, because after all, it's totally your choice which rule you want to use at what time. Okay, and now this guy, you can say eventually it's producing a 2. Meanwhile, for this one, we'll say I'm going to exp plus exp, and this becomes the 3, and this becomes the 5, and now the yield, the thing you get, if you write it as a string, it's 2 times 3 plus 5, so same string, but grouped as a tree, we get and this is, of course, the wrong grouping. So here we have a situation where the grammar allows 2 or more distinct ways of parsing the expression. Such a grammar is called ambiguous. And it is an example of bad grammar engineering. So first of all, a given language doesn't have a unique grammar, absolutely not. So in finite automata theory, we saw it's absolutely not true that for a given regular language there's a unique automaton. There was, however, a unique minimal automaton. There's no such thing here. There's all kinds of different grammars. There's no sense in which there's a minimal one. Okay, And so when you have a grammar like this, we say this is a bad grammar. It's ambiguous because it produces the right strings, but it doesn't group them the right way. So you have already some more structural idea in mind than just this is a sequence of letters. So it is possible to redesign the grammar so that it is not ambiguous. And the point is, at least in this case, there exist languages for which no unambiguous grammar is possible. And we call such languages inherently ambiguous. So importantly, being ambiguous is a property of a grammar. And it might be that the language is okay, you just designed the grammar poorly. So you should redesign the grammar to make it unambiguous. And this is done in a standard way. So in the notes that I've given you, I have given an unambiguous grammar for this language of arithmetic expressions, which will prevent you from producing the tree where the 3 plus 5 is bound more tightly than the 2 times 3. So it's worthwhile studying that and seeing how this is done. But since this is the elite class of everybody who can do things twice as fast as normal people, we are going to cut out these simple examples and do more complex things. Okay, so let me pause for any quick questions. No questions. Who's the co-host? Is it Haneli? Have we
I
lost
am. There
her?
are no questions in the chat.
Very good. So we now move to designing context-free grammars. Techniques for designing. So we started out, our very first example was a grammar that produced a language A to the N, B to the N, which was one of our favorite non-regular languages, so that we saw right away context-free grammars are going to give you significantly more power. So let's do a bunch of examples. And then I have to move on to do a lot of topics about context-free languages. So first, I want to produce this language. And this is easy. You just have to make sure every time you produce an A, I'm producing 2 Bs. And then when I'm tired of producing things, I just wipe out the non-terminal. Okay, so this is just using the idea that every A is matched with 2 Bs. So I use matching. You see there's a kind of recursive aspect to these rules. You generate a string like this, but that string has an embedded non-terminal, which can then be used for further generation. And at the end, when you want to terminate the process, you just wipe it out. So these are very, very simple and basic grammars. So first thing you see, context-free grammars can count. They can count the A's, they can count the B's, they can check numerical properties between the A's and the B's. So if I wanted A to the 5n, B to the 17n, I could define it easily with a context-free grammar. Next, I would like this language. And so this is x in sigma star such that x equals x reverse. This is the language of palindromes, words that read the same backwards and forwards, like repaper, which we remember we proved that this thing was not regular. So this is a typical matching problem. So we need just a start symbol. I don't think we need any other non-terminals. And basically we say, well, if it reads the same backwards and forwards, as soon as you start with an A, you better end with an A. And if you start with a B, you better end with a B. And in the end, you can just end with an A. The middle letter doesn't have to match anything. But you might also want even numbered, even length strings. And there you have it. Okay, example 3.
There is a question.
Yes,
Yeah. She's asking, for all examples, we assume sigma equals AB, right?
for these 2 examples, not for all examples. Obviously not for arithmetic expressions. Yeah, for these 2 and the third one, the alphabet is AB. And technically I should write down terminal symbols are this, non-terminal symbols are that, start symbol is this, the rules are that. But I'm just going to write down the rules and let you see what all those things are. So the language, it's the set of words with number of A's. So this notation means number of A's in X equals number of B's in X. So this is not just first all the A's and then all the B's, so you can easily count off, but there's some A's and some B's coming later on, and then maybe more A's and some B's. And in the end, when you do the counting, they all have to match up. So this is unfortunately more of a pain. Okay. Right. Let's define. So how do we approach a problem like this? So let's define d of x to be the number of b's in x minus the number of a's in x. Okay, so we can say the language we want is the set of x such that d of x is 0. So if you want, you can read d as discrepancy or something. So supposing x is an L, and so I'm going to say let u be the shortest prefix of x such that d of u is 0. And suppose u starts with b. Right? So this shortest prefix might be all of x itself. It might be that the very first time you end up with a string that's properly balanced is when you finish the string, but maybe not. Maybe somewhere earlier it was already balanced, right? And suppose this, so we've got x and we've got u, and u starts with b. So now we know u must end with a. Okay, I'm asking why. You can worry about that yourself. Why can't you also end in B? Okay. So now we've decided that U has to have this form, B V A. And so this string V must also satisfy D of V equals 0. Because if it doesn't, then U won't, right? So X has the form U and then something else that finishes it off. Since D of U is 0, this implies D of Z is 0. D of X is 0, D of U is 0, so D of Z better be 0. Otherwise, Z will be an unbalanced string. This is a balanced string, and X cannot possibly be a balanced string. So now we see if X has this form, then all these things are also in the language. So if we have something that's generating strings in this language, we realize what the pattern is. It has to be S, well, empty string is a good thing, but it has to be something like that. So here is the B that starts it, the A that ends it, and then another string that's in the language. Or it could have been the whole thing reversed. It could have been starting with A, in which case it had the shortest prefix that's balanced had to end in B, and then after that there's another string that has to be in the language. So you can see this guy will generate the language. Or just to prove to you that, or demonstrate that the grammar is far from unique, I could have designed a grammar like this. Okay, either of these grammars works, so nothing unique about the context-free grammar for the given language. Okay, so we've done a bunch of languages. And then I'll say every modern, that means after the Beatles broke up, so after 1970, every modern programming language is defined by a context-free grammar. And indeed, something much more restrictive than a generic context-free grammar, but we will explain that later. One of the questions on assignment 3 is every regular language is a CFG. So of course, CFGs can do many more things, but in particular, they can do everything that a regular language can do. If you want to express it as a context-free grammar, you can do that. And in fact, it would be a very structured, special kind of context-free grammar called a left linear grammar. So this thing is also on your assignment, and you will work it out exactly. So now I'm going to rapid fire throw some information at you, which maybe is not the most gripping, but it's important because we have to get through a bunch of preliminary stuff. So we're going to make the following claim. A CFG is said to be in Chomsky normal form. CNF, not to be confused with CFG. There are lots of TLAs in this subject. TLA stands for three-letter acronyms. So it's said to be in Chomsky normal form if every rule has this form. So I'm using uppercase letters to stand for non-terminals and lowercase letters for terminals. So these are non-terminals. And A is a terminal. We do not allow, oops, we do not allow rules like this. Except for the start symbol. So some books will say we don't allow that even for the start symbol, and then they will prove that for every context-free language, there exists a context-free grammar in Chomsky normal form that can produce exactly the original language, possibly without epsilon. Whereas if you allow only the start symbol to do that, then you can say also I can produce epsilon if you want. So I will claim a theorem here. Every context-free language is generated by a context-free grammar in Chomsky normal form. Okay, so I've actually written a proof of this in the notes, and you can go through it in some detail there, but I'll just sketch the idea here. So you basically systematically get rid of bad rules. So for example, if I've got a rule like this, A goes to epsilon, where A is not the start symbol, this is a forbidden rule, then throw it out. But then you'll say, oh my God, that screws up the grammar because maybe I needed to be able to eliminate the A. So what you do is, and look at any rule with A on the right-hand side. For example, you might have a rule like this. B equals something alpha 1, and then there's an A, and then there's some other string alpha 2, and then there's another A. Okay, maybe there's a rule like that with a bunch of A's thrown in. So what you do is add all possible rules with some of these A's removed. So you have to add B goes to alpha 1, alpha 2, and then as before, but also B goes to alpha 1, A, alpha 2, alpha 3. So those are all the things with one of these A's removed. Then you have to look at all the rules with two of the A's removed, all the rules with three of the A's removed, and so on until you finally got all possible things that you might, where you might have removed A going to epsilon. You can kind of simulate that by directly having these rules simulate that effect. Okay. So so there are many other kinds of things you have to do. Of this type. In my write-up, I discussed them all. But there's one kind of rule that is interesting. So let's say you figured out how to get rid of all the rules where you go to epsilon and all the so-called unit rules. And now you've got a long right-hand side. So let's say you've got A goes to x1, x2, x3, xn, where each of these belongs to, so there's maybe a long rule. The right-hand side is supposed to have only two things, and they're both supposed to be they're both supposed to be non-terminals. So what you do is you replace this with A goes to x1 A1 and x1 goes to little x1 if x1 is in, if it's a non-terminal. If it's not a non-terminal, then you just leave it like that because that's a valid rule. And then what do you do with this A1 thing? So A1, you say that's x2 A2 with an analogous step there. A2 goes to x3 A3 with an analogous step there. And so you see all these AI are new non-terminals. So we've systematically replaced this long rule with a whole bunch of short rules. So in the end, in Chomsky normal form, you have very simple rules. Either one non-terminal goes to two, or one non-terminal goes to a single terminal. Not at all an efficient way, but it's a great conceptual thing to prove some theorems about context-free languages. And it's a non-trivial fact that even though this looks super limited, it's actually powerful enough to do anything. And there's a systematic, even an algorithm to do the translation from a generic context-free grammar to a Chomsky normal form grammar. Now, of course, if I was going to give you mindless, stupid exercises, I could tell you, homework, convert this context-free grammar into Chomsky normal form. This is the kind of thing I leave to robots. So I'm not going to ask humans to do assignment questions like that. Okay, any questions about Chomsky normal form?
Not in the chat.
Not in the chat. But even if these details, I'm not particularly expecting you to remember these details, I just want you to see that you have a lot of freedom in restructuring the grammar. Restructuring the grammar, of course, doesn't mean you get to change the language. When I say restructure the grammar, I mean things that modify the grammar, but preserve the language. So now let's look at some things analogous to what we did with regular languages. So let's look at closure properties. Of CFLs. So first, supposing L1 and L2 are context-free languages, then L1 union L2 is a context-free language. And what's the proof? Supposing S1 is the start for G1 and the language of G1 is L1, and supposing S2 is the start symbol for G2 and the language of G2 is L2, and let's say we can easily do this by renaming non-terminals. Let's say the non-terminals of G1 and G2 are disjoint, so there's no clash about which one we mean. Then we can simply get so take all the rules together and add S goes to S1 and S goes to S2 as two separate rules. Obviously, this is going to produce the union language because you can either go to S1 and then produce a string in L1, or you can go to S2 and produce a string in L2. So this way you've got them all covered. So I do emphasize which rule you choose is up to you. And the language is defined by saying, consider all possible choices of how you use the rules. That's what defines being in the language. So some people still have problems reading quantifiers. So the language is defined as all possible ways of choosing the rules and leading to a string of pure terminal symbols. So L1 dot L2 is also a context-free language, where this means what you might think it means. You take a word from L1, you take another word from L2, and you concatenate them. And I'll just write the idea. Above we said either you can go to S1 or you can go to S2. Here we'll say you go to S1, S2, stuck together. So S1 will generate a word from L1, S2 will generate a word from L2. So that's easy. L star is a CFL if L is. So what do? Add a new start symbol. We'll call it S prime and add the rules. S prime goes to S, S prime, or epsilon. So this S will generate something from L, and you'll have S prime that can fire up again and produce another copy of S, and can keep going and produce as many copies, and finally you can peter out. Or you can just die right away, in which case you get the empty string, which has to be an L star. Okay, so these are all super easy proofs because we had the power of grammars rather than fiddling with automata. Okay, so concatenation, union, and Kleene star are all preserving context freeness. But now CFLs are not closed under one intersection and two complement. So here we see we've got a more powerful language and we lose some of our algebra. And this is going to be a theme. As we say, I want a more powerful language to do this and that. I said, yes, okay, here it is. But now you've lost some of the elegance that you had with the simpler languages. Okay, so let's see examples of why this is true. So a to the n, b to the n, c to the m is a CFL, because you can basically produce this using the CFL mechanism, and then you have another non-terminal just producing as many C's as you want. So is a to the m, b to the n, c to the n. Right, so here you say, I don't care how many a's there are in front, it's not correlated at all with the b's and c's, but these guys have to be matched. Okay, so now let's call this L1, and let's call this L2. L1 intersection L2 equals, well, this guy says the A's and the B's have to be matched. This guy says the B's and the C's have to be matched. So if you're in both languages, all three have to be matched. And this is not a CFL. So how are we going to prove that? Tomorrow. So what we're going to do is introduce a new pumping lemma for context-free languages. And with that pumping lemma, we will be able to prove various languages are not context-free. But just from the intuitive point of view, you can see this guy, you can have some non-terminal, and that's generating A's and B's that are nicely matched whenever it's producing anything. But then the C's are kind of buffered from you by the B's. So how can you control that? And similarly, you say, okay, if I try to keep the A's and B's matched, then if I try to keep the B's and C's matched, then the A's are buffered from you. And how can you control what's happening to the A's? So you can't control both at the same time. So this is not a CFL. Later on, I'll give you automata theoretic argument for it. Okay, so this language, just like A to the n, B to the n was our favorite example of something that's not regular, A to the n, B to the n, C to the n is our favorite example of something that's not context-free. And many things will actually be reduced to this. Okay, so note, let's call this language L. Is not a CFL, but L complement is a CFL. And I'll give later on many, not many, but a few more examples of languages that are definitely not CFLs, but whose complement is. So these are all illustrations of it is not closed under complementation. You kind of know that it can't be, right? Because if it was closed under complementation and it's closed under union, it would have been closed under intersection. So the fact that it isn't closed under intersection with a concrete example is already proof that it could not possibly be closed under complementation as well. Okay, so make sure you understand that argument. But now I would like to say something on the positive side of the closure properties. And this is a very, very, very important fact. If L is a CFL and R is a regular language, then L intersection R is a CFL. So taking two CFLs and intersecting them will give you something that's not a CFL. But if I take a CFL and a much tamer thing like a regular language, then intersecting them will preserve the property. And this is one that's easier to see from an automata theory point of view rather than from a grammar point of view. The other closure properties were very easy to see from a grammar point of view. Okay. So I have talked about closure properties. And I'll say fact. There is an algorithm to look at a grammar, a context-free grammar G, and decide if the language of that grammar is empty or not. It's easy to write grammars that actually don't produce anything. For example, I have a start symbol and I give you no rules for S, and you can give you rules for all the other non-terminals, and it's pointless. They're not going anywhere. You can't get to them. That's a stupid example of a grammar that doesn't produce anything. Okay, but there are also other ways in which a grammar can fail to produce anything. So it might be that you never actually get rid of the non-terminals. You don't have rules that say wipe out all the non-terminals. And then you'll generate maybe long strings which will still have non-terminals in them, but by definition, this is not in the language. So then in the end, you ask, well, what is in the language in such a case? And the answer is nothing. So you can write big, complicated grammars with language of that grammar is empty set. And the point is there is an algorithm that can just look and decide. So please think about this yourself. There's nothing, there's no rocket science in it. It's just your typical graph type of algorithm. Okay, so I'm wondering whether to take a break here. I think I'll take a break now and we'll restart at 12. So break till 12. Then I will tell you about the CKY algorithm.
Maria suggested a fix in the notes. On the third example, at the beginning of the class, it should be du equals 0. I think he just wrote du, such that du, like the sentence was incomplete. Yeah, of x such that du.
Yes, thank you. Too excited. Does everybody know what dynamic programming is? And screen sharing. Great, welcome back. So we're going to describe an algorithm for checking the following question. So you're given a word, you're given a grammar, and I'm asking you, hey, did this word belong to this language? And this algorithm is going to work by dynamic programming. So it works on general context-free grammars, even ambiguous ones. And it is actually um, got a lot of elaborate decorations that are involved, which I'm going to skip by telling you, assume G is in Chomsky normal form. Okay, so if it's not in Chomsky normal form, there's still stuff you can do. Um, and more or less this algorithm as it's given works, but there's some more bookkeeping, and the bookkeeping is not exciting. So we're just going to pretend it's in Chomsky normal form. So I said Chomsky normal form grammars are maybe hugely expanded and clunky. Yeah, well, deal with it. So we've got a Chomsky normal form grammar. We now know that any CFL has a CNF description. So now I give you a word and I ask you, is this word in the language? Seems like a basic question, and the answer is yes. There's a decision procedure, which is cubic time in the length of the word, which, by the way, is not good enough for practice. So just for theoreticians who care that this is a decidable question. Okay, it's in fact what they call efficiently decidable in theory, but practical people like things to be linear time. And all modern programming languages are designed with a much restricted notion of what of allowed languages, and are guaranteed to actually be linear time checkable. In fact, linear time parsable. So anyway, but we're doing the generic thing. So this is going to be your typical dynamic programming algorithm. So what are you given? You're given a grammar which has a set of non-terminals of variables. It has a set of terminals or alphabet. It has a start symbol and a set of rules. We use the letter P for the set of rules because people in this world call them productions, because they produce strings. Anyway, so so this is given. This is part of the thing you're trying to reason about. And then the input to the algorithm is a word with n letters. So these AIs, so this thing is in sigma star, and AI is in sigma. All the AIs are in sigma. So I'm going to look at this letter by letter. And so the basic idea is work bottom up. To construct a possible derivation for W. Okay. And so the basic idea is we start by asking, well, how did you get each individual letter? Since it's in Chomsky normal form, to get a specific letter A, we must have used a rule of the form A goes to A. Because in Chomsky normal form, the only way you're getting a non-terminal, the only way you're getting a terminal is a rule like this, because these are the only rules that produce terminals. All right, so I can define inductively a two-indexed family of subsets of V. So we define inductively a two-indexed family of subsets of V. And these are defined like so. So I'll call the, so two indexed means two indices. So there's an I and a J, and these I and J are numbers, and I is less than or equal to J. Okay, so I less than or equal to J. So we'll define a family like this Xij, and the definition is it's the set of non-terminal symbols such that starting from A, I can eventually, so the star means possibly with many steps, not just the first step, I can get the piece of the string from position I to position J. So is this definition clear? So for each consecutive piece of the string, I'm asking, how could I have gotten this piece? Okay. Well, how am I going to compute all these things? Well, basically, supposing I somehow computed all of them for all i's and j's, and the whole word has length n, in the end, I'll ask, okay, what's in the set x1n? So tell me all the things that could have generated the whole string, and then I'll look in that set and say, ah, s is there, okay. Well, that means I have a derivation of this word, right? Clear? So the point is to build up these sets inductively, and that's where the dynamic programming aspect comes in. So we'll start out by saying xii is the set of A in V such that A goes to A sub I. It's in Chomsky normal form, so you can just look at the rules and say, which of you guys produces this letter? All right. So now you've got all of them. You've got x11, x22, x33, x44, and so on. Okay. So um, and so then when we come to compute xij, we assume that we have already computed xik and xkj for all k between I and j. Right? So all the shorter substrings. And then basically you look at all possible ways of gluing them together, and that'll give you the string xij. So if the non-terminal B belongs to xik and C belongs to xk plus 1 j, and A goes to BC is a rule in the grammar, then we put A in xij. So this is the key step. So this is what you have to make sure you understand. So we're building these things up inductively. So let's say I've got x11, x22, x33, x44, x55, and so on. Then I'll say, how am I going to get x12? And I'll say, x12. So that's basically x11 and x22 stuck next to each other. So I'll say, who produces x11? Who produces x22? Now, do I have a guy that produces the non-terminal for x11 and a guy who produces the non-terminal for x22 and a rule that goes like that? Well, then that guy produces x12. There may be nothing, of course. And so now you keep growing this set in all possible ways. So whether the thing is ambiguous or not doesn't matter. You'll just get multiple derivations. And in the end, you can ask, so who produces X1N, or who produces the whole string? And if S is one of the guys producing the whole string, you're home free. Okay, so would anybody like to see an actual example, or can I leave it to you to read the example in the notes? I realize, it's good pedagogical practice to give an example, but this is, a completely straightforward algorithm. Keeping track of the bookkeeping is important. I have put on the website an explicit example worked out for a string of length 5 and the Chomsky normal form grammar written out explicitly. And you can see every stage in the computation, even color coded. So you can see which was computed from which stage. And I think rather than, watching me do this fantastically boring task of filling in a table, a dynamic programming table by myself, I suggest you look at this note and see the explicit example, because I think that will help you understand it. Yep. Okay, good. So there are other algorithms that one can ask about context-free grammars. Is there an algorithm? So you can ask, you give me a grammar. Does that grammar produce anything at all? Or is it just a stupid grammar that doesn't end up producing anything? So this is decidable. And the idea is very simple. So you look at all the non-terminals that actually produce a pure terminal or a pure sequence of terminals, and you say, oh, we'll call this non-terminal a productive one because it actually produces something. Then we go back and say, okay, if you are a guy that produces only productive things on the right-hand side, then you yourself are productive. But now productive things means terminals or already designated productive non-terminals. And you keep iterating until you find out all the productive terminals, non-terminals. At the end of the day, if you say, is S productive? Well, then you know it's producing something. There has to be some strings in the language. The language is not empty. You can do a similar modification and look for cycles in an appropriate graph that I leave you to think about and ask, is the language of G infinite? This is also decidable. So hence, obviously, it's also decidable whether it's finite. So you might want to know, oh, well, is the language of G equal to all of sigma star? Right? Very natural question. This magically turns out to be undecidable. So what happened in context-free grammars is you push the envelope on the power of the formalism and you've fallen over the edge of undecidability. So some questions are still decidable. Some questions are undecidable. For regular languages, everything in sight is decidable. But for context-free languages, this was a surprise when I first learned this. And it's absolutely not obvious. And so, of course, I have to teach you what undecidable means first, and then I have to do a clever reduction to prove this fact. But we will do all that. So this is a foretaste of things to come. So if you think context-free grammars have been boring so far, there's an exciting thing lurking around the corner, namely the undecidability of this simple, innocent-looking fact. And first sight, you think, oh, surely there must be some way of checking this. And it's just not the case. It is provably impossible. Okay. So other things like that are also provably impossible. Give me two context-free grammars. Is their intersection empty? So for one of them, it's empty. I mean, to know whether just one context-free grammar produces an empty language, yeah. Intersection of two, that's undecidable. So many things that you would think shouldn't be so difficult actually turn out to be impossible. Right ho. Another thing I have to mention in passing is that this whole dynamic programming algorithm is the start of a topic called parsing, which I'm not going to talk about, but it's a hugely practical topic, and it leads to a much more subtle classification of context-free languages into much finer classes. And this is something heavily studied in a compiler class. And this subject has reached such a high state of understanding that really nobody has to write parsers anymore, because we have automatically produced parser generators. So these parser generators, you can feed in the description of the grammar and it will output the code to solve the parsing problem. A nice high order function. So there we go. All right. Now I want to uh, wrap up. So I have wrapped up the linguistic side. I now want to discuss the automata side of this subject. And this leads to a subject called push down automata. So this is an old-fashioned word, push down. It was what we in modern language called a stack automaton. Because what's a stack? You push things on it, and then you pop things from it. So it's basically NFA plus stack. And I should emphasize one stack only, not two stacks. Okay, one stack, no more. Okay, so I want to motivate the basic reason why am I talking about these things. So I'm going to state a theorem which has a long proof. It takes like maybe an hour and a half to explain the full proof, and it's filled with details that you have to get right. So I've never been thrilled by this proof, but I'm glad somebody did it. So I'm not going to do it, but I'll state the theorem because it's super important. By the way, I emphasize this is NFA. So there's non-determinism basically built in to push down automata. There are also deterministic push down automata, but they turn out to be limited and not equivalent to non-deterministic push down automata. So theorem, every context-free language can be recognized by a PDA. This stands for push down automaton. This is the standard abbreviation. It's not personal data assistant. It's push down automaton. Okay, every CFL can be recognized by a PDA, and every language recognized by a PDA is a CFL. More succinctly, I could have said, a language is context-free if and only if it is recognized by a PDA. So this is the motivation. And it gives you an automata theoretic perspective on context-free languages. And sometimes it's easy to do something with a grammar and hard to do it with the PDA, and sometimes it's the other way around. So it's not always obvious which path you should follow. And especially this is important in final exams, because I've asked questions like, prove this thing is a CFL, and the people sweat trying to find a grammar for it and they can't. Whereas a PDA to recognize it would have been easy. Or conversely, people sweat trying to get all the details right in a PDA when a grammar would have been easy. So you need your judgment to be sharpened about which is the way to proceed, but they are equivalent. So here we go, enough propaganda. Let me tell you what a PDA is. So you have a set Q of states, and this is finite. You have an input alphabet. And this is finite. But now you have a stack And on the stack, you can put additional symbols that are not part of your input. So this is called the stack alphabet. And this includes the input alphabet. So you can put anything in the input on the stack, but also maybe special other symbols you can put on the stack to mark things. You have a transition relation or transition function, if you want to describe it like that. Sorry, so I want to introduce some additional notation. Sigma sub epsilon is sigma union the special symbol epsilon, and gamma sub epsilon is defined to be the stack alphabet union the special symbol epsilon. So the reason I'm introducing this is because sigma, these things can make epsilon moves. Okay, so delta says I will read an input symbol, or maybe I'll just make a jump because that's why it's sigma sub epsilon. Oops, sorry. I will be in a state, yes. And I will read either an input symbol or make a spontaneous jump. And I will look at what's on top of the stack. Or maybe I won't. That's why there's an epsilon here as well. And then I have a finite set of possible moves. That's why it's non-deterministic. So I can change my state. So I can go to some new state and I can fiddle with the stack. So I can modify the stack. So I can't modify the stack in a completely wild way. I can basically do stack operations. I can push one symbol onto the stack, or I can pop the stack. Okay. There's a start state, and there's a finite set of accept states. So I should mention that there are two notions of accepting, but I'll tell you that in a minute. So here this notation P sub F means finite power set. This is what I was writing as 2 to the power A before, but 2 to the power A allows me finite or infinite subsets. Now I'm insisting finite branching possibilities. So you basically start in Q0, stack is empty, read the first symbol, and start moving. So it was slightly inaccurate there because perhaps you can make some epsilon moves before you actually start reading. So at each step, the automaton may and I emphasize may, doesn't have to do any of these things. It has possible things that it can do. So what are the things it might do? It may look at the input and the top of the stack. So you see, it now has infinite memory because it's an unbounded stack. You can keep stacking things on it, but you have somewhat limited access to it. You can't just kind of scan the whole stack and make some decision. You just say, oh, I see what's on top of the stack, and based on that, I can make some move. So it can look at the input and the top of the stack, and then change state. So that's the next thing you can do. It can then change state. it can pop or push on the stack, pop the stack, or push something on the stack, or both. And then move to the next symbol. These are the actions. And of course, it's a non-deterministic machine. So we're going to introduce a notation for describing the transitions. So I will write A, comma, B, arrow, C. And this means A is seen on top of the stack. B is the next input symbol. Oh, sorry, I got this backwards. A is the next input symbol and B is seen on top of the stack. And then you pop the stack. Whoa, that's doing weird things. Pop the stack and replace B with C. So pop the stack, B is gone, push C. So that's the most generic move you can make. So A may be epsilon. What does this mean? Don't read the input. B may be epsilon. In that case, you're not popping anything off the stack, just push C. And B remains on the stack. Whatever was on the stack stays there. C may be epsilon. Then you're just popping the stack and not replacing it with anything. So any of those things may be epsilons. So let me show you some simple machine, some simple automata. So as before, we use the convention of double circle for a start state. We use an arrow to indicate, sorry, double circle for an accept state, an arrow indicating a start state, and we have arrows going to the next state. So this is the machine that's going to read 0 to the n, 1 to the n, and recognize it. So what is this machine starting out doing? It does this. It says, I'm ignoring the input. I'm ignoring what's on the stack. First thing I'm doing is I'm stacking the special symbol $, which is not in my input alphabet, but is in my stack alphabet, onto the stack. This tells me, hey, I've initialized the stack with $1 in it. So that now with the $ symbol, so that I know when I reach the end. Okay, so I'm allowed to load the stack with symbols like this to mark special positions. Over here, I have a transition label like this. So in our notation, it says, you see 0 on the input, you don't care what's on the stack, you just push it. You just keep pushing zeros onto the input. Then You see 1 on the input, you see 0 on top of the stack. Well, you pop the stack and you move to a state that says, now I'm no longer stacking zeros, I'm popping ones. So this brings you to state Q3. And what are you doing in this state? You're repeating the move that got you there. So you say, okay, I'm seeing ones in the input, I'm matching them with zeros on the stack. And every time I see a 1 in the input and a 0 on the stack, I pop the stack and I go to the next symbol. So basically, you're counting off. You've stacked all the zeros and now you're counting off. Do I get exactly the same number of ones? And then if life is good, at one point you will say, oh, I see I'm at the bottom of the stack. How do I know that? I see this dollar symbol that I stacked right in the beginning. I suddenly see that this is now sitting on top of the stack. That means all the zeros have been popped, and I just move to, I don't fiddle with the stack anymore. I don't push anything. I just pop this last symbol and I come here and I accept. So why was this an accept state? Because epsilon is also in the language, so you just want to accept that right away. Now you might say, wait a minute. Let's say I've got 5 zeros and 6 ones. So then I'll pop here, all the zeros will be popped off, and then I'll say, I'm not looking at the input anymore. I see a dollar, I'm just going to an accept state. Yeah, you can do that. You'll end up here, but you are required to go all the way to the end of the input. So at this stage, you'll say, I'm in Q4. I have an input symbol not processed, which is 1, and I have no transition written down. I am jammed. So that's actually reject. So when there is input and no valid move, it counts as a reject. What if I see another random symbol like a club suit? And then I'll say, wait, there's nothing like that in my alphabet. So it just rejects. Okay, so this is actually a special example of a deterministic machine. But in general, you can have non-determinism. So let me show you a non-deterministic machine. So did everybody understand this framework and how to follow along the transition diagram? The structure is more complicated because there's a lot more action happening in each transition. I think I put these notes on the course website, which are much neater than what I'm actually writing here. But let's do this language. So this is a 3-letter input alphabet, ABC. And you have to have some number of A's, some number of B's, some number of C's. I, J, K are all greater than 0. And either I equals J or I equals K. Now, how are you going to do this? This is where you use non-determinism. So you stack the intuitive idea is simple. You say stack all the A's and then guess, is it the B's that are going to match or the C's? So if the B's match, then you check the B's, just as we did before. If it's this, if you guess that the C's are going to match, then just read the B's and dispose of them. You're not bothering to stack them or anything. And when you come to the C's, then start carefully matching. Okay. So by the way, writing down these full pictures gets more and more annoying. And I don't want to ask you to write down in detail the transition diagram of a PDA very often. There is one question like that on assignment 3, but mostly I'm very happy with descriptions of the kind I just gave. Okay, still has to be clear, but that's how the description goes. Okay, so basically this one really has to do non-deterministic guessing. So as you may have guessed, deterministic pushdown automata are strictly weaker than general pushdown automata. You cannot take a general pushdown automaton and get a deterministic version of it. In fact, the languages that can be recognized by deterministic pushdown automata are very special, and they're called deterministic context-free languages. We will talk about them tomorrow. For the moment, I just want to show you non-determinism actually being used in a non-trivial way. And this is where I wish I could just project this picture rather than having to redraw it for you. Okay, so here's your start state, Q1. And step one is you say, I'm going to load up the stack with this special dollar symbol on the bottom. This is a thing one does quite often because you want to say, have I really seen everything that's on the stack? If you put this dollar symbol, you know, I have really emptied out this whole stack. All right. And in this phase, you are just stacking the A's. So this is how you describe just stacking the A's. You see A on the input, you ignore what's on the stack, you push the A on the stack, not popping anything. So A, epsilon, arrow A. Every transition is seeing an A, popping, pushing it, pushing it, pushing it. So at some point, you've got to the end of the A's and you make a wild guess. And you have one of these exciting transitions labeled epsilon, epsilon, epsilon. It says, I don't look at the input, I don't look at the stack, I don't mess with the stack, I just go. So there you are. This state is called Q5. And the other possibility is you go up here. To a state called Q3. And this is also an epsilon, epsilon, epsilon transition. At this point, the machine just decides, I'm just going for it. And I'm guessing either I should go to Q3 or Q5. And what are you doing in Q3? Well, you're doing this. So what does BA epsilon mean? It means, I see B's on the input, A's on the stack, pop them and move on. So basically you're checking, do the B's and the A's match up? And then, how do you discover that they match up? You find, oh, there's no more input and the stack is empty. No more input doesn't really mean no more input, means I don't need to look at the input. You just come here and then you accept. And in this state, if you're seeing C's, you ignore the stack, you don't bother to push the C's, you just say, yeah, C's, I don't care, just count them till I get to the end. Whatever number of C's there are, I'm going to accept it because the A's and the B's matched. And on this side, it's the opposite situation. So this Q5 behaves a bit like that Q4. It says B's, I don't care about them. I'm going to read them and throw them away, not bothering to push them on the stack. And at some point I'm figuring, oh, I've reached the end of the B's. You might say, how did you know you reached the end of the B's? Well, you don't know. But if you guess incorrectly, you'll reject. But the acceptance condition is, like all non-deterministic things, there has to be some valid accepting path. And so that brings you to Q6. Q6 is a bit like your Q3. Here you're carefully checking. Do the C's and the A's match up? So seeing C in the input, seeing A on the stack, popping the stack and moving on so that the next A on the stack matches the next C on the input. And then if I see, I've got to the end, then I can go to a nice accept state. Okay, so I've described this machine, including the informal description and this formalism in my notes. So I'd like to make some important general points. Acceptance only happens at the end.
There is a question from,
Yeah.
I'm not sure if somebody answered it, but he's asking if Q1 should also be an accept state. And then somebody says, I don't think so. As it says, I don't think so.
Should Q1 also be an accept state? No, because because the empty string is in the language, that's correct, but you'll accept the empty string anyway, right? Because you have epsilon transitions all the way to an accept state. Don't know why my OneNote crashed on me. All this technology is wonderful, except when it crashes. My chalk never crashes on me. All right. So important general points. Acceptance only happens at the end. You can't jump and say, I'm going to an accept state, there's more input left, but I don't care. No, you have to read it. So even when you say non-determinism means you get to make choices, one choice you don't have is you can't just decide, I'm sitting in my accept state and declaring accept when there's unprocessed input. And then two, yeah, there's non-determinism and you can do all kinds of, you have choices, but a machine, a PDA cannot decide to jam. Oh God, this thing is jumping around wildly. Cannot decide to jam when there are valid moves. Okay, so I can't just say, oh yeah, part of my non-determinism is I've decided to jam and reject now when there is a good move that I could have made. Okay, so is that clear? So that is, in a nutshell, examples of pushdown automata. So in my notes, which were written for my darling 330 students, I have actually traced through how the stack looks as it processes a thing. So you can read that example if you want. And this brings me to the fundamental theorem. So now some remarks to make. There is an alternative notion of acceptance. And this is called, so there are no accept states. So it's a different kind of automaton, slightly different, mostly looking very similar, but it really is a different kind of automaton. There are no accept states. We accept if the stack is empty at the end of the input. So it's literally a different kind of automaton. Okay, so it's not like you can say, well, it has some accept states, but also if I'm at an empty stack, then it's accepted. No, either you're designing a machine that accepts by accept states, or you're designing a machine in which there's no such concept as accept state, and the acceptance condition is at the end of the input, your stack is empty, and that's it. And it's not, again, not obvious at all, but either one kind of machine can simulate the other. So there's no real difference. You can use whichever is more convenient for your purposes. In the assignment, I've actually asked you to design a machine which accepts by empty stack rather than by accept state. And sometimes it's convenient, sometimes the other one's more convenient. So the PDA I've asked you for on the assignment is ridiculously simple. So don't sit there and stare at it for hours saying, my God, this can't be right. Prakash surely wants to torture us more than this. So it isn't like that. It is actually a simple answer. Just checking that you read the formalism. Okay, so now let me make some more or less informal remarks. We can intuitively see a to the n, b to the n, c to the n cannot be accepted by a PDA. Why? You stack the A's, count off the B's, and damn it, the B's have gone, the A's have gone. How are you going to check that you have the same number of C's? And now what? Okay, you cannot check the C's now, right? So that's very sad. So if we only had two stacks, we could accept a to the n, b to the n, c to the n. Because what would we do? We would stack the A's on the first stack. Then we start reading the B's. We pop the A's and stack the B's onto the second stack. So at the end, we'll say, the B's are finished. The A stack is empty, so they matched up, and now I've got all the B's stacked up, and I can check them against the C's. So with two stacks, I can do A to the n, B to the n, C to the n. Okay, so this tells you two stacks is more than context-free languages. I haven't proved the theorem, but it is a fact. A one-stack machine is equivalent to having a context-free language. And this one is not a context-free. Again, I haven't proved that. That's tomorrow when we do the pumping lemma. What about A to the n, B to the n, C to the n, D to the n? How many stacks do I need?
Ronald says 2. Owen says 2.
Very good. So you don't need 3 stacks because you push all the A's on the first stack, and then you push the B's onto the second stack as you're counting off. So now the B's are stacked up on stack 2. Then you check off against the C's, stacking the C's back on the first stack, which is now empty and waiting, and so on. So you don't really need more than 2 stacks. Okay, so you might have thought, oh, for this I might need 3 stacks, but of course it's not true. 2 stacks is enough for any number, a to the n, b to the n, c to the n, d to the n, e to the n, f to the n. 2 stacks is enough because every time I finish checking off one thing, I've also emptied a stack which I can use for the next check. And here is a non-obvious fact. A PDA with 2 stacks is universal.
There's a question from Asa. In general, can a machine with 2 stacks accept any language that a machine with more stacks?
I'm about to answer this. A PDA with 2 stacks is universal, i.e., it has the same power as a Turing machine. and can compute any computable function. So counting stacks is not a good measure of complexity, because after one stack, two stacks, boom, you've got them all now. So in fact, in the old days, people explored different kinds of machine models and seeing which one was more powerful. So then they said, what about a machine with a queue? It's not quite the same as a machine with a stack. What about a machine with a counter? It's not quite the same as a machine. A counter means simply something that can count. So it's basically one integer variable. You get to increment and decrement. A machine with one counter is more powerful than a DFA for sure. It can do some things that a one stack machine cannot do, but it cannot do some things that a one stack machine can do, etc. Um, a machine with two counters turns out to be universal. So at some point, people realized that this is barking up the wrong tree to look at different data structures. What about a DFA with one queue? How does that compare? Well, it's not exactly the same as a machine with one stack, but if you had two queues, then it's actually as powerful as a Turing machine, etc. Um, and what people realize that what you need to do is worry instead about computational complexity and count steps and count space and not be fiddling around with one stack versus two stacks. So instead of this picture of counting things in terms of auxiliary data structures, we now work in terms of this whole subject called complexity theory, where we look at the asymptotic resource consumption of algorithms as a way of classifying the power of different problems. Okay, so good. That is the end of today's sermon. No, I meant lecture. Tomorrow, we will look at the pumping lemma for context-free languages and possibly some more exciting examples of CFLs. All right, very good. So I will see you tomorrow. If you have questions, you can send me email. I've put up assignment 3, which will be due the following Monday. Assignment 4 will be a short one, and it will be due on Thursday. And then your final exam you will get the final exam Thursday at midnight. It's like those Harry Potter books where you had to line up to wait for the book to come out at midnight. So final exam will come out at midnight, and you can have 72 hours to do it. Okay, see you tomorrow. Bye, everyone. Stop sharing.